Okay, 9.4, we're going to continue on with testing, hypothesis testing, but now we're going to take two different means. So two different means, we're going to first start off with the dependent samples today, and then the next video, 9.5, we'll talk about independent samples. So we're going to identify, explain, and compute differences of paired data and estimate the p-values of the test and make some conclusions based off those p-values. Now, what I mean by paired values is we have dependent samples. So the members of each pair have a natural matching of characteristics. So in other words, we'll take members, certain people, objects, things like that, and we'll look at them before and after. Maybe we've put some sort of like treatment to them. So maybe kind of like an experiment where to take information before, run an experiment, give some sort of treatment, take some information later, and figure out the differences. So one would be like a weight loss program. So take the weight before and take the weight after a certain diet. Okay? Those are paired data. They're dependent samples because we're changing the individual. Advantages of using paired data sets: it reduces the measures of variability, so no outside things can kind of kick into that. Or you're dealing with the same person, so there's no, well, this sample could have had this feature into it, whereas this sample has that feature into that. May reduce the dangers of introducing extraneous or uncontrollable factors, okay, kind of the same thing. Increases accuracy of statistical conclusions. Okay, so in a random, so theorem 9.1, don't need to remember the 9.1 fact, but in a random sample of n pairs where the differences are now d. So you're going to come across this d, and it basically means the difference between the first member and the second member of each paired. It's going to approximately follow the normal distribution for the mean of all the differences. So this is the population mean of all D's, or differences. And what I mean by difference is person before, person after, subtract the two, there's your difference. Okay, the following is going to be true. We're going to use T, so now you're going to use a degrees of freedom, and it's going to be the number of objects. This D bar is the average of all the differences, the population of all the differences, and we're going to use the sample standard deviation divided by the square root of n. It basically, if I were to write it out a little bit nicer, it's going to end up being this standard deviation divided by the square root of n, just like it did before for all the d's. Okay, where d bar is the sample mean of all those differences, and SD is the standard deviation of all those differences. Okay, our assumption that there is no difference from the paired data. So the null hypothesis would be that there is no change amongst the pairs. So that means that the difference of one number to the next number always works out to be 0. So the mean of all the differences is equal to 0. We can test that with the left-tailed, so the mean is smaller than 0. Right-tailed, the mean is the bigger than 0. But since we're doing a t-score, these two are pretty much the same idea. They're both one-tailed. And then we could change or test the fact that there's a change, so there's a difference other than 0, whether it's positive or negative. Okay, so here we go. Here is my data. I've got patient A, B, C, and D. So that means n is equal to 4. I've got 4 people. We have a diet plan that's being used. Person A is 177 pounds before. After the weight loss program, they're 162 pounds. Okay, B to before and after, C's weight before and after, D's weight before and after. I'm going to test whether or not this weight loss is effective at a level of significance of 5% or 0.05. So what I did is I added a third column for D. So it doesn't really matter which way you subtract these, you just have to make sure you're consistent. If we're going after minus before, the 162 subtract 177 gives me negative 15, negative 1, negative 2, and 1. Take these 4 differences, nothing else, but take the 4 differences, put them into your calculator onto list 1, and run 1 var stats. Okay, if you run 1 var stats and you get L1, D bar isn't going to show up, it's going to be X bar. It will work out to be negative 4.8. 4.25. So the average of these four differences worked out to be negative 4.25. Now, make sure you pick the sample standard deviation. That's the one that's going to be S of x, is a 7.27. Okay, we're going to test that it is going to give us significant weight loss. So that means the mean of all the differences is going to be less than 0. Again, that just tells us we're going to use one tail. Okay, our null hypothesis is that there is no change. Our alternative hypothesis that there's going to be weight loss, so that means it's going to be less than 0. And then we're going to use all that to find your t-score. All right, so the mean of differences from our calculator, negative 4.25. The population, which is 0, this is always 0. So you can basically just stick with that number on your numerator. The standard deviation away from is also on our calculator. The square root of 4, because there was 4 people, you get a t-score of negative 1.17. Okay, so you're going to look at the t-score. Remember, the negatives aren't in there, so we'll just change it to a positive. Look in the table under degrees of freedom of 3. 1.17 would fall to the left of the lowest value in the table. Okay, so the lowest number on that table, again, we're looking at the student's t table, is 1.423. I better double check that. Okay. Isn't going to be the left of that. It's actually going to be in between, not the lowest value of t. It's going to be between the t values of 0.7560. So that means this p-value is going to be between, yep, still going to be bigger than that number, but it's going to be less than 0.250. Okay, now make sure that you're looking under the one-tailed spot. So I'm going to have to adjust my probabilities here when I'm doing my comparison. I'm going to compare that to 5%, right? So I've got my p-value of 0.250 and 0.0125. Okay, there's my alpha. 25% is going to be bigger. In fact, I put a decimal in that wrong spot, 0.125. In fact, this 0.125 would be bigger. So that means that we cannot reject, or we're going to fail to reject, the null hypothesis. So we can conclude that this weight loss, we can conclude that we cannot reject the hypothesis that there's no significant difference in the weight loss before and after the diet. Weight loss before and after the diet are essentially the same. So basically, our data wasn't statistically significant. We couldn't throw out anything. All right, so here we go, page 535, 135, 11, 13, and 15. Again, they're all odd, so you know the answers are in the back of the book. I would suggest doing quite a few of these just because you're not used to seeing that D bar and the standard deviation that way. So